as mentioned, my name is Aisha. I am currently a PhD candidate at McGill in experimental medicine, and I also work as a marketing brand strategist with Dispersa, which is a Montreal-based startup. So I'm just going to share my screen. All right. Everyone's able to see the screen, no problem?
Yes.
Excellent. All right. Let's skip here. So let's get right into it. Right off the bat, what is data visualization? It seems a little obvious. Oh, it's visualizing data, but what does it really? What does it really include? So here's an example. Is this data visualization? If you're in the chat, you're welcome to share your comments. Do you think this is data visualization or not? So you can type it in the chat, yes or no. Yes, excellent. Yeah, this is data visualization. We have information that's spread out on the map. We have some key data points. It is a form of visualization. Okay, what about this? Is this data visualization? I mean, it's data. We're looking at it. Does this count as data visualization? No, that is correct. What is the difference between this image and this image? Why is this data visualization and this not? If anyone wants to either in the chat or someone wants to speak up, you're welcome to. Yeah. So basically, first it's easier to understand. So a lot of good points here. I mean, we can have data visualization that is data visualization is very difficult to understand. We'll see some examples of that later on. But the key, and we'll get a little bit more shortly, is that there are data visualization. The actual image or visual representation is based on the data in some way. Here, we're just looking at data rather than the visualization itself being based on the data. So here's an example that is clearly data visualization. You might have seen some of these figures before, whether it is in scientific papers in particular, for example, for those of us who are in science. What about this one? Here's a nice little screenshot from Twitter. We've got little icons. We've got some numbers next to it. This is data visualization. You can put it in the chat as well. So interestingly enough, this actually is not data visualization. Just like the giant, beautiful Excel table we were looking at earlier, here we're just looking at information. These icons themselves actually have nothing to do with this number. So we could change this number and these icons wouldn't change it. We're really just looking at data. It's more visually appealing, sure, but it's not actually data visualization. And in this case, we have a nice infographic and we have some data visualizations in the corners here. So data visualization is the graphic representation of data through pictorial design. So we have the data, and the actual graphics or the things we're looking at needs to be a representation of that data rather than just something that's visually interesting. So we're going to break this workshop into two main parts. First, we'll be going over the principles of good graphics. And then later, we'll talk about all the different types of graphic methods that you can use to represent your data, and it'll really help build your toolbox. So first off, why do we use data visualization? There are many reasons, depending on the application, but it helps us comprehend information quickly. We can identify relationships and patterns in a way that just looking at a spreadsheet will not allow us to do in a trivial fashion. We can easily communicate information to others. And of course, there's visual appeal aspect as well. On the right here, you can see a really pretty looking data visualization that's a map of the solar system. So this individual took a whole bunch of data that NASA had for all the celestial bodies in our solar system and made a really, really cool data visualization out of it. You probably won't use this graphic as a reference for your next physics paper, but it is quite visually appealing and is based off of the actual real data that's been collected. All right, here's an example of why we visualize our data. So you might have a nice data set. You get some statistics on it, maybe some mean, maybe some correlations, maybe some standard deviations. What's interesting is that these four plots all have the exact same statistics. And when I say the exact same statistics, I'm referring to these five that are shown on the slide here. But as you can see, by making quick plots of this data, they look quite different. It'd be perhaps quite surprising if you're conducting an experiment and you saw a dinosaur popping up in your data set. But the idea of visualizing data is it allows you to rapidly spot patterns in your data that you wouldn't otherwise be able to pick out just by looking at the statistics and the numbers themselves. There are many different ways in which data or information can be encoded in a graphic. There's hue, which is one of the key aspects of, think of it as color. There's size, so for example, something bigger might, something that's larger might represent a higher number or value. There's value, which you can think of it as the lightness or darkness of a color. There's shape, position, and pattern. These are just some of the ways in which information can be encoded graphically. So this gets into what makes for an effective data visualization. So these are the 10 points that I want everyone to really absorb, internalize, and remember for every future plot that they ever make in their life. These are the 10 commandments of data visualization. First, thou shalt identify thy message and tell a clear story. 2, know thy audience. 3, thou shalt consider thy medium. 4, thou must keep it simple. 5, thou must reduce chart junk. 6, thou shalt not mislead the reader. 7, thou shalt not abuse colors, and there is far too many examples of this. 8, thou shalt use visualization types that best fit thy message. 9, thou shalt avoid 3D plots on static media. There's some common offenders that we'll talk about later. And then 10, thou shalt not trust default formatting. Very important. We'll talk a little bit more about each of these points in a bit more detail, but this is the summary. So first, thou shalt identify the message and tell a clear story. When you're designing a figure or a data visualization, visualizing your data, the objective is you're trying to communicate something. So you have to decide what is your message and how and what kind of visualization method or plot type, etc., would best emphasize or express this message. Every figure that you develop or design should have a very clear role, and there should be a tight bond between the message and the visual. Are there any questions so far, by the way? If there are any questions throughout, and please feel free to just leave a message in the chat and I'll be able to jump to it as soon as possible. The second is to know your audience. So you need to design your figure with your audience in mind. Are you talking to a group of experts? Are you talking to a group of experts? Are you talking to a layman audience or the general audience? Is your figure going to end up in a nature journal, or is it going to end up in a BBC article? These are all very important considerations in terms of how you design your scientific figures. Is this just for you alone, where you're just doing exploratory data analysis and it'll be kept private so you don't have to worry too much about formatting? 3, you must design with your medium in mind. So how will your data visualization be used? How large will it be? How long will the audience interact with it? So for example, if you're putting a figure on a scientific poster versus on an online article where you could have infinite zoom in to look at all the details in your figure, is it something that people need to understand in a couple of seconds, or is this the type of figure that someone will sort of really try to digest over the duration of a few minutes? So here's an example. Which of these two figures on the left or right do you think would be more appropriate for a scientific poster? So you can just type left or right in the chat. Right. Yeah, I would agree with that. Left does look cool. Yeah, I mean, and if you had an online journal article and you were sharing this data, you could potentially include this one that has much more detail, because again, you can zoom in, you can really take time to digest it. But in a scientific poster, you don't really get that much more information. If you're trying to communicate a key message quickly in a format where someone's standing 2 meters away from your plot. That's what we're looking at. Yeah, that's true. It does depend on your message. I mean, in this case, if they're just trying to show the difference in, say, the trajectories of two different groups, like say the things shown in blue and things shown in red, the summary of that data is still captured. The essence of it is still shown in the simpler plot. But yes, I agree. It depends on the application. In this case, scientific poster, I would argue the simpler is better. 4, thou shalt keep it simple. Focus on the patterns in your data. In a given figure, you don't have to plot everything. Just focus on what is interesting. The idea when you're trying to visualize the data is to also help reduce the data complexity. So don't feel like you have to put everything on a single chart. Often, you're better off splitting data into multiple charts, simplifying colors, or even changing the chart type that allows you to better digest or better emphasize certain patterns that you're trying to demonstrate. So, for example, if we look at a really beautiful line plot like this, can anyone actually understand what's happening here? We got a lot of different colors, we got a lot of different individual data sets here. It's a complete mess. 5, thou shalt reduce chart junk. All graphic elements that you put in your plot should have meaning. So we're here defining chart junk as all unnecessary or using visual elements in the figure that do not improve the message or they add confusion. A principle to keep in mind is to improve the data to ink ratio. So if you're adding something to your figure that's not improving understanding or not conveying some type of information, you should ask yourself, should this really be there? 9 out of 10 times it probably shouldn't. In science in particular, the message and the clarity of the message trumps the beauty. So you might have something that's very visually appealing, but is confusing to understand and get that message. That's not to say that your graphics should not be visually appealing, they certainly should, but you have to always remember that the message and the meaning should be foremost. So here's an example. This is the same data set plotted in 2 different ways. Which one do you find easier to read and digest? The one on the left or the one on the right? So again, you can type it in the chat. Right. Absolutely, absolutely. I mean, if we're looking at this figure here on the left, first of all, we have this pretty ugly yellow background. We've got all these unnecessary grid lines. There are too many different colors on the plot, overlapping, can't follow anything. And if you're selecting a giant data set and just running a line plot, this might be, along the same area of what your default might look like. However, by splitting it up into these subfigures, you can still have some of your background data, but you're highlighting the key trajectory line for each of these points. It's much clearer to understand, and it's not as dependent on color. If you tried to print this in black and white, you'd basically be hopeless. So here's a mini challenge for everyone. I want you to try to remove, if you're looking at this column chart on the right, I want you to try to remove as many markings from this chart as possible without losing information. So if you have a sheet of paper in front of you, take 1 or 2 minutes and try to resketch this plot using as few lines as possible, or as little ink as possible, or graphite in the case of using the pencil. So have a go for it, and then in about 2 minutes, we're going to talk about what are some of the unnecessary elements in this figure. Okay. So let's go through some of the things that are unnecessary here. All right, so we have a couple of suggestions. First, from Lawrence, the chart can be reduced from 0 to 20, 0, 25, 50 increase. Yeah, so reducing the number of tick marks on the y-axis is what I understand. And the background can be changed to white, absolutely, to clearly visualize the grayscale of the bit. So as I understand, basically reducing the number of ticks on the y-axis, removing this background. I also have removing the outer border on the top and right. Yeah, that's another excellent suggestion. Just the top error bar. I don't think the bars are necessary, only the error bar on the top of the bar. Yeah, that's another great suggestion. Excellent suggestions. So here's an example of a simplified one, a super minimalistic version of the same plot that conveys the same information. Now, it's not to say that you should get rid of all of these axis bars or that super minimalistic is always the way to go when you're doing your figures. But the idea here is to understand what marks here, what what is it in the figure that's actually conveying the information. So as was suggested, you have just the top of the bar, we have the error bar. We can even technically remove these little tags here, so we've done that here. We have fewer ticks, we don't really need that many of them, and we have information specifying the categories. Again, that's not to say that you should remove all of the markings in this case, but these are really what's conveying the information. Does anyone have any questions about this or anything else? Did they arrive at something very different? Okay. Number 6, same but add x-axis labels. If you're not too many data points, actually add them. You mean like the tick marks around these? Actual data points. Oh, I see. So like yeah, you can do like a column scatter. And that's a very smart idea. Often it's often good to include that additional information. Though in the original plot, we didn't actually have that for the individual data points here. But yeah, I agree that if you're actually designing a figure, that's a very smart thing to do. We'll talk about that in the second part of this workshop as to why that can be particularly useful. Okay, number 6, thou shalt not mislead the reader. So the very important is to represent your data accurately. So when you're having any representation, the chart needs proportional and directly proportional to actual numerical quantities. So you don't want to oversimplify the data to the point where you don't have sufficient context to really understand it. You have to be careful and not deliberately truncate the y-axis. It seems like an obvious thing, but pie charts need to add up to 100%. And I'm making the argument that we should always avoid dual axis line charts. This may or may not be an unpopular opinion, but here's my argument. A dual axis line chart, the idea is where you have the 2 data sets, and on the left and right, you'll have 2 different y-axes that have some different units, and you'll be plotting that data on top of each other. Here's an example. In this case, I haven't actually, there's not the actual drawing of the units on the side, but if we imagine having the exact same data set, in these 6 cases, it's the exact same data set, but we can manipulate those y-axes in the dual axis chart to tell basically whatever story we want. So in this case, here we have a relatively flat looking orange line versus a sort of a skyrocketing blue line in this case, a blue data set. And the message from this figure is very different from the message in this last figure, where they both appear relatively steady. The issue with these types of charts is that they're far too easy to manipulate, to basically tell whatever you want. And so in general, I believe they should be avoided. 7, thou shalt not use colors. Colors should always have a purpose. So when you're designing or creating visualizations for your data, you really want to try to restrict your color palette as much as possible. And in fact, in cases of scientific figures, it's worth trying to design your figures in black and white or grayscale first before you whip out the color palette. If you're making multiple charts, let's say subfigures, multiple subfigures in one larger figure, keep your color palette consistent and the style consistent for all of the charts. Another consideration when choosing colors, sometimes colors will be used to differentiate data sets, is to keep in mind that there is a sizable minority of the population, particularly amongst men, who have some form of color blindness. And so if you're looking at doing a red-green heat map to look at your gene expression data, perhaps it's worth trying a different color set to actually be able to represent that, and so everyone can actually read what you're trying to communicate. In general, darker or brighter colors read as more, so you want to make sure there's that logical connection. Let's say you're doing a grayscale heat map and you have, say white to black and as a gradient. Generally or intuitively, most will see, the bolder color or the darker color as more. Either way, you need to specify it, but you want to make sure that whatever representation you're using is intuitive. You can use gray to denote neutral or unimportant material. You want to keep in mind white space. And in general, every color you use should be there for a reason. So here's an example of an RNA, a gene expression data set. We have the original on the left, and we have a basically the equivalent of what someone with a severe form of color blindness might see. How easy do you think it is to really get information from this data if you have color blindness with this data set? It can be quite difficult for some individuals. If you change that data set, let's say to use a red-blue color scheme instead of a red-green color scheme, now you can see that even in cases of for severely colorblind individuals, they're still able to get information from this plot. So it's one of those considerations to keep in mind when you are designing your figures. 8, thou shalt use visualization types that best fit thy message. So the graphic type you choose influences your message, and every type of plot communicates or emphasizes an aspect of your data. You can also consider how transforming your data might affect your message. So here's an example, a little exercise. Suppose we have the world population data stratified or divided by continent. Which of these plots would match which message? So if you want, you can have a go at this and then type your answer in the chat. So for example, if you think a bar chart would best emphasize message A, then you can put 1A. Each of these, I mean, there's a little bit of subjectivity, but each of these matches best with one of these messages. So there's a one-to-one mapping. Have a go at it, and let's see what you guys think matches or best matches each message. Everyone have a go. Okay, well let's here we go. 1B, 2C, 3A, 4D. All right, does anyone have the a different 3A? Yeah. A, B1, C, D4. Okay, so we have some agreement. So let's look at these. 1B, a bar chart. Asia has the most people. Bar chart would make certainly the most sense. You sort these columns by or each bar by height and amount, and you'd emphasize, okay, Asia has the most people population-wise. Conversely, a majority of people live in Asia, so the idea of a pie chart is to sort of emphasize proportion. And so a pie chart would better emphasize that message. A line chart might show that the population is increasing in all the continents, whereas if you're trying to emphasize something like growth rate, then you want to transform your data, and then you can then use a line chart to emphasize the changes over that. And as you can see that everyone who's participated has an agreement in terms of which of these chart types matches which message, even though you're working with the same data set. So consideration is, again, when you're trying to plot your data and visualize your data, what is the message that you're trying to get across? What is it you're trying to communicate to whoever else is actually viewing that message? So here's an example. 9, thou shalt avoid 3D plots in static media. 3D plots are for interactive media only. So if you have an interactive data set online, you can play with it in a web browser or an electronic device, then it can be great. However, they should almost never be printed on paper or to be viewed in a static sense. 3D plots are unjustified, for example, particularly unjustified in data with 2 axes. So you might have seen in Excel, for instance, they have some options where you can have a line chart, or you can take that same line chart and make it 3D. This should never be used, and quite frankly should be removed as an option from the software. The other major issue is if you do actually have 3 axes of 3-dimensional data, that data in the back is easily obscured, and it's very difficult to actually perceive or read any information. So for example, if we're looking at this figure right here, it's very difficult to actually read or understand any of these data points, particularly whichever bars are at the back, the perspective-wise of this figure. So here's a fun figure from the late Steve Jobs, with one of his old presentations looking at the US smartphone market. Okay, so in the chat, let's see if we can list some things that are wrong with this chart. How could we improve this chart? if we were making a pie chart for Steve Jobs? Divide other, so its pieces are smaller. It's 3D. Image has a weird angle, patterns instead of colors. Portions are represented, remove 3D. Okay. Some of these are very good suggestions. So let's go through some of them. You guys can continue sharing your ideas as we talk about it. So first of all, remove 3D. Yeah, absolutely. As I said before, you have a data that can be represented in 2D, and there's 3D, effects added for really no reason. So first of all, this needs to be a 2D plot. Let's say dividing others, you could divide others, though in a pie chart, you generally want to avoid having too many individual pieces. And let's just suppose this is the data that we're working with. It's at a weird angle. Yeah, absolutely. Which is this green wedge at the bottom, and other, which is this purple wedge. Which one looks bigger visually? I mean, this green one looks a lot bigger. I mean, Apple's doing great, even though amongst the other among other US smartphone manufacturers, they have a larger market share. So it's quite visually misleading. So they're misleading the reader. Proportion, yeah, so proportions don't seem represented. That's correct. It's not colorblind friendly. Yeah, that's correct. And in fact, all of these are super bright, super saturated colors that it's actually quite difficult to read and pick out these different wedges. Even for someone who has no color blindness issues, it's a little bit jarring. So changing the color palette, maybe emphasizing specific wedges if that's what they want to communicate. So for example, making some of these other wedges dimmer and then highlighting Apple's wedge if that's what they want to focus on. Or if they wanted to highlight their biggest competitors, they could highlight Apple and RIM, for example. Obviously, this breakdown has changed a lot in the last 10 years. Some of the colors are very similar. Yep, exactly, changing the color palette. Something else to consider is that these wedges are not actually sorted by value or by size. So in a pie chart, generally speaking, you should be ordering your wedges in order of size. So in this case, it would be your blue wedge, then your purple wedge, then your green wedge, and then your orange, red, and pink. So essentially, so it's easy to understand the sequence of the data. Okay. So here's an example of a good use of data visualization. This is a browser-based interactive semantic brain visualization tool. So this is you basically go on there online and you can drag around and actually explore which parts of the brain are activated in response to or associated with different types of words. Now, this is not something that's intended at all to be visualized on even a static slide as I've done here, or let's say printed in a scientific paper, but this is something that you're meant to interact with. And this is a great example of how you can take advantage of 3D media. Finally, number 10, visualizations require customization, 9 out of 10 times. So any plotting software has some sort of default settings, so size, font, colors, styles, tick marks, axis scales, etc. These default settings are often designed such that they're okay for any plot, but they tend to be best for almost none of them. And almost all plots require at least some manual tuning. So for example, whether that's changing the colors that are by default selected, whether that's changing shapes, whether that's changing the axes, number of ticks, removing excess lines, etc. To really emphasize how each of these softwares have their own unique style, can anyone guess what software this plot was made in? You can just type your answer in the chat. Excel. Yep, exactly. And Excel has a very, it's got quite a unique default style. If you plotted something with the default settings in ggplot and R, you'd see, again, something quite unique. If you did something in Matplotlib or in MATLAB, again, it has very unique default settings. And most of the time, you're going to want to change some of these settings to really make an optimal visualization for your data. One of the key messages I want everyone to take away from this workshop is visualization type should suit the data and should suit the message that you're trying to communicate. So you have to consider, if you have a data set, you're trying to decide, okay, what kind of plot or plots would I need to represent this? What is it that you're trying to get across and what kind of data you're presenting? Do you want to show relationships? Do you want to show distributions? Are you trying to emphasize proportions, perhaps changes over time? And you also have to consider what are your variable types. Are they discrete? Are they continuous, categorical, spatial, structural in some way? There are many references, reference catalogs of different data visualization types if you want to read more about these. But today we'll go over one of the main ones, especially in addition to a few special ones. So some of these I'll skim through really quickly. I think most people here should know what these are. Histogram is for one-dimensional continuous variable and can show data over an interval. It's great for showing a rough view of a distribution, say a probability distribution. However, you have to keep in mind that it's quite sensitive to the actual bin width that you select. And you have to be careful because you can mask potentially interesting patterns, or alternatively, you could mislead by having too narrow of a bin where it just looks like static. Density plot is an alternative. This is better at showing the distribution shape because it's not affected by bin width. However, you can only show a limited number of distributions in one plot. So if you want to, let's say, overlay the distributions to compare the distribution of one group to another, you can do this with 2, maybe 3 groups. You might be pushing it, but if you want to compare the distributions of, let's say, 5 to 10 different groups, stacking on density plots is really not the way you want to do it. We also have box and whisker plots or box plots. This is looking at the distribution that's summarized through quartiles, and this takes up a lot less space than histograms or density plots because you can have multiple categories side by side. However, their simplicity can hide details in the data distribution, so you have to carefully consider whether or not this is masking important information or if this is reasonable for the data that you're working with. Violin plot, which is one of the examples that I used earlier. This is to break down what a violin plot is. Actually, quick question: has anyone here actually seen a violin plot in the wild before? Message in the chat. Yes, yes, yes. Okay, that's good. So just to summarize, generally they'll include a mini box plot inside it, or a version of a box plot, and then you'll have the density plot to mirror on either side of it, which is a way to represent the distribution of that data as well. So this is great because it can show more information about the distribution than just a normal box plot. But of course, you have to be aware as to whether or not this information is relevant or not, because you are communicating more in your figure and more information. There's also, of course, a higher risk of noise. So if it's completely unnecessary, then it may not be worth including, but it can convey some additional interesting and useful information. So here's a little challenge. Are these groups A, B, C, D, and E the same? So these are 5 data sets, and then we've generated box plots for each of them. And at a quick glance, these all look identical. But if we look at, say, column scatter, we can see that no, these are actually quite different between these 3 of them. And so in this case, depending on how much, perhaps it might be odd to have a data set that looks strictly like some of these. But the idea is that these box plots can hide potentially interesting or relevant information in your analysis. If, however, we did a violin plot, we could actually see that there are quite major differences in the distributions between these data sets. And it might be something that's useful to know, particularly at the exploratory data analysis stage. For column charts, I don't think I need to go over these too much. They're very simple, easy to understand. The general public also really will generally understand how this works. But they do hide a lot of information like the distribution of the data, and labeling and clutter can become problematic if you have too many bars, as we've seen just in that stack bar chart that we were working with earlier today. Finally, you have to remember the axis must start at 0. You can't start your axis here, for example, at 3, and then over-exaggerate the difference between these 2 values. Scatter plots, again, we've seen it before, great for looking at correlations. However, it can be difficult if too many data points are close together, and so in that case, you might want to look at something like a contour plot or a density plot instead. A different one, this is often used more so in for public communication because they can often look cool, is a bubble chart. And this allows you to show the distribution of 3 or 4 variables at once. So you have variable 1 on the x-axis, variable 2 on the y-axis. You then have the actual size of the bubble corresponding to a 3rd variable. And you can go even crazier if you wanted and encode a 4th variable inside the color of the dot, or like the darkness of the dot. And these can be great for interactive graphs where there aren't too many data points. However, if you have too many bubbles, it makes it almost impossible to read and they have very limited capacity. And in these cases, if you're generating these plots, the bubble area is what has to be directly proportional to the value and not the radius, because you can very easily mislead or over-exaggerate the differences between values. Line graphs, no need to really talk about this too much, but more than 3 to 4 lines overlaying is far too difficult to read in the mode. Heat maps, we've seen a couple of heat maps today, and this basically just visualizes variation through coloring, keeping in mind that this is a lot less quantitative because we are approximating differences by color. Our eyes will not be that good at detecting small differences between colors or shades that are very similar to each other. Now here's a fancier one, a chord diagram, which visualizes the relationship between entities. These can be really visually appealing. However, over-clustering is an issue, and there's also the issue of how readily people will understand these types of plots. So here's an example of such a chord diagram. This is a data set that looks at global migration rates. And so we're looking at sort of the amount of migration from one continent to another continent. And this is a nice way to visualize the flow, this relationship between these different groups. Parallel coordinate plots is a way to look at multivariate numerical data. These again become really, really cluttered quickly, but they can help identify relationships between different variables in a data set. A variant of that is something called an alluvial diagram, and this looks at showing flow in changes in proportions in the data. So, for example, if we're looking at favorite color between males and females, we can visualize that the proportions between these two overlapping categories in a plot like this. So this would be the equivalent table, and here's how we might visually represent it. Network diagrams, which you may have seen if you're looking at, let's say, gene networks, or you're trying to represent some other kind of network-based data. These are great because it's an intuitive representation of a data type. However, you can't really encode that much information in it. They become very hard to read, and some of you may have come across figures in the past that look like hairballs, where you have way too many nodes, way too many links, and the only message that you get from that figure is, wow, that's a lot of connections. The appearance is also quite sensitive to the layout algorithm. So it's great for simple models, but really complicated things, you have to ask yourself, does it actually communicate everything, or does it show like, wow, look at all this data I collected? You also have arc diagrams, which is a different 2D based method or a different method of representing network diagrams. These can be good at highlighting clusters. However, just like network diagrams, they have major issues if you have too much data. And it can be very difficult to read. Choropleth maps, or you think of it as a heat map on a geographical region. I'm sure we've all seen these before. This is a very common method to visualize data over a geographic region. So it's like a spatial distribution. And it can be nice to identify patterns in data related to geography and location. So for example, if we're looking at COVID-19 infection rates across the island of Montreal, you might look at a heat map and say, okay, well, here's a hotspot. As with heat maps, there are some issues as well. You can't, for example, accurately read or compare colors on a map, particularly two colors that might look somewhat similar, but they're not right next to each other. It'd be very difficult to compare them. And larger regions are more emphasized over smaller ones, even if they have a lower population, for example, depending on how you are normalizing your data. And then finally, we have pie charts. So these show proportions or percentages between categories by dividing a circle into segments. This can be great for giving a quick idea of proportional distribution in a data set. So say I'm trying to emphasize that X percent of a particular population has some characteristic or falls into some category. However, it's a really poor method for accurately comparing across groups. It cannot be used to show more than just a very small handful of values, and it's hard to distinguish proportions that are close in size. So 9 out of 10 times, I would argue that pie chart is the wrong choice for your figure type, with a few rare exceptions. And generally, if you have a lot of values that are very similar to each other, doing a bar chart will be a much better way to visualize that data instead of a pie chart, even though marketing people love pie charts.